All right. Everything that you say mean to me at this point could be heard by other people.
Your mom.
Did you say your mom?
Brenda.
Brenda.
She's the sweetest person in the world.
Brenda, what's her last name?
Costello? You're funny. Okay. I mean, there's a chance she could have been something else, but she's not. She's a gospel. Alright. Okay, so we are talking about logarithms today, and like I said, the first thing we're going to learn is the connection between logarithms and exponents. So when you understand the connection, that will help you to be able to write them both in each other's form. So if you're given a logarithm, how to write it as an exponent. If you're given an exponent, how to write it as a logarithm. So those three things we're going to take care of like right off the bat. So here's the thing. The other day I told you there was two really good ways to solve exponential equations. One is if you can make those bases the same. That's an awesome way. And that's what we did the other day. We created those bases to be the same, so we dropped off the bases. Remember that? Really simple. The other way to solve exponential equations is using logarithms. So we can't understand how to use that method until we understand the connection between exponents and logarithms. So that's what we're doing today, understanding the connection between the two. Now, in the future, why would I use logarithms over what I've already done, making those bases the same? Because with exponential equations, you can't always make the bases the same. And if you can't make the bases the same, then what, you just can't solve it? No, you got to involve logarithms. The same exact thing is true when it comes to solving logarithmic equations. Sometimes you can solve logarithmic equations by dropping off the logs, but then other times you can't. So what do you do in that case? Well, if you understand the connection, you can take that logarithm and rewrite it as a what? Exponent. And then you can solve. So we got to understand the connection between the two because we're going to use them moving forward, okay? So here's the connection, the base. Okay, the base of the log has to be the thing that you keep straight. The base of your logarithm becomes the base of your exponent. Okay? So, for example, when I look at this logarithm right here, it says log base b of a equals x. Now, base b, so that little bitty value down here below the b, that's going to be called your what? What did I just call it? Log base b. So that's going to be called our base. The a value here, this is generally referred to as your argument. Your argument. So be prepared to hear that. And then this right here, the x value, that is either your solution, or if you're thinking about it in terms of exponents, they call it the exponent, or technically, if you had values here, it's your logarithm of base b of a. Okay? So, when we read this, we say log base b of a equals or is x. Log base b of a is x. Log base b of a equals x. Got it? Now, here's the connection. If I wanted to take that logarithm and I wanted to rewrite it as an exponent, if I want to understand the connection between the two, here's the connection. The base of your logarithm becomes the base of your exponent. So base b of your logarithm is going to be the base of your exponent. Well, if that's the base of the exponent, guess what it's got to have? It's got to have an exponent, right? And here's how it works. To change a logarithm to an exponent, you got to do a loop. You got to do a loop. Okay, here's what that means. If I want to rewrite log base b of a equals x as an exponent, I'm going to do b to the x power equals a. b to the x equals a. That's the connection. So I got to keep in my brain the base of my logarithm and the base of my exponent are connected. It's the same. Then you do the loop. And it's that easy, okay? Log base b of a equals x. It's the same thing as b to the x power equals a. Okay? Let me prove it. Go down here to number 1. What's the base of my log? 3. Okay, so look at this, guys. 3 to what power equals what?
9.
Is that true? Does 3 squared equal 9?
Yes.
Yeah, 3 squared means 3 times 3. So there's the connection. If I want to take a logarithm and rewrite it as an exponent, the base of my log becomes the base of my exponent, and then we do the loop. 3 to the second power equals 9. 3 to the second power equals 9.
What if it doesn't like equal?
It has to,
It has to.
because the connection is there. It can't not be the same. You can't have a situation where you could say, hey, this logarithm, it won't rewrite as an exponent. It has to. They have to be equivalent, because that's always going to be a connection between the two ideas, logarithms versus exponents. They're always connected, so it has to. It has to equal. You follow? So I could literally go through here and just write these as fast as you let me, right? How would I rewrite this one? Y'all help me out with this one. 6
to the third equals 216.
to the third equals 216. Look, guys, the base of my logarithm becomes the base of my exponent, and then we do the what? We do the loop. And I don't expect you guys to draw the loop every time, but maybe a couple times on your paper just to kind of make sure you understand how this works. But 6 to the third power equals 216, and that's absolutely true. 6 times 6 times 6, absolutely 216. Okay, so understand, we're not just doing something to be doing. It's reality. The logarithm can be rewritten as an exponent because they're connected. Okay? It's not a fluke. It happens every time. So, for example, number 4. How would I rewrite this one? 2 to the fourth equals 16. Absolutely true. Okay, go over here to the left. How would I rewrite this one? 7 to the equals 1. Anything to the 0 power is 1. Remember the way I explained it to you? As you consider going from positive exponents to negative exponents, how it goes from being in the numerator to flipping and being in the denominator? Well, when it's to the 0 power, it's like the one time where it's on top of itself. And what's anything divided by itself? 1. That's why anything to the 0 power equals 1. Okay? Now go on down here to number 5. How would we rewrite this one? 4 to the negative second equals 1 over 16. Again, 100% true. What's 4 squared equal? What's 4 squared equal? 16, right? So how do I make it when it's negative? I flip it 1 over 16. Absolutely true, okay? They're connected. Look at number 6. How would I rewrite it? No, remember, just do the loop. 9 to the what? 9 to the 3 halves equals what? 27. Okay? Not as familiar with that one, but it's a fractional exponent. So technically it means the square root of 9 cubed. Okay? That's what that means. The square root of 9 cubed. Remember, the denominator is the root, square root of 9 cubed. That's what that's saying. So 9 cubed is what? What's 81 times 9? 729? So it's the square root of 729. 27. Okay? Does that make sense? Now, reverse it. The next group of problems, they want me to go from an exponent to a logarithm. Same thing. If I was saying the base of my exponent or logarithm becomes the base of my exponent, reverse it. The base of my exponent becomes the base of my what? Logarithm. What's my base of my exponent here? So I'm literally going to write log base 14. And then I'm going to follow the same loop. Watch. Log base 14 of what? 196 is what? 2. So log base 4 of 196 equals 2. Same process. All you got to keep connected is the base of your logarithm, the base of your exponent, and then do the loop. Okay? Aiden, you look like you might have a question.
No.
And again, this is completely true. Isn't 14 squared 196? Absolutely. Okay? They're connected. They're always connected. Like Deanna asked a second ago, is there ever a time where it's not? No, it's always connected because they're connected. All right? I mean, there's no better way to explain it than just to say they are connected. They'll always be connected. Okay? Now, let's go over here to number 8. 3 to the 4th equals 81. We want to rewrite it as a logarithm. Let's go. What is it?
Log base 3
Log base 3
81
of 81 equals 4. That's it. Look, base of my exponent becomes the base of my log, and then you do the loop. Okay? And that's all there is to it. Okay, let's go through these pretty quickly then. How do we do 10? Log base 36 of 6 equals 1/2. Done. Just like that. Every time. Okay, I'm going to skip number 9 for a second. Go to number 12. What we got? Log base 8 of 16 equals 4/3. Huh? Last one before I do number 9. Log base 2 of 1/8 equals -3. And that's how you do it every time. Okay, last one. What is it?
12 of
Say base 12. Say.
oh yeah, base 12
Thank
of 12 equals 1.
All right. Again, I know that I don't want to be annoying with this, but remember, say base 12. Log base 12 of 12. Okay? So, the reason I want to do this one last is because I want you to notice something, because it kind of sets us up for what we're about to do. Whenever your base matches your argument, what's your solution? It's going to be a 1. That's always the case. If I ask you guys, hey, what's log base 3 of 3? 1. What's log base 7 of 7?
1.
What's log base 100 of 100?
1.
Y'all get my point?
Yeah.
When the base matches the argument, your solution is 1. Yes, sir.
What if one of them is negative?
Same. Actually, we won't have a base negative. Because remember, we talked about how exponents are never what? The base of an exponent will never be negative. Okay? So you will never have a negative base of a logarithm. Okay? So therefore, you will never, if that's negative, they'll never be matched up. Okay? So with logarithms, you won't have base negative. Okay? Good question though. Now, here's why I even point that last one out, and I wanted to save it to the end. Go to the top of the back page. There are 2 types of logarithms. There are these ones called common logs, and then there's some that are called natural logs. The only reason that they have a second log called a natural log is because in certain situations in life, like even as far as like investing money or watching some bacteria grow, there is a value that is so common in nature that they gave it its own specific value. Okay, it's called E. And E, which is termed Euler's number, is about 2.71828. And it has its own logarithm. They call them natural logs. We're going to talk about those later. But when you see log, that is called common log. You see, in this next section of problems that we're about to do, I used to have to do the method that's on the back that has a big X on it, because my calculator would only work in common log. And I want to explain what common log is real quick. And the reason I did number 9 last is because you're going to see. Go to your calculator and look down the left column, and you should see a button that just straight up says LOG. I want you to push it. And then I want you to put 10 inside, and don't push enter yet. Don't push enter yet. Okay, listen. When we talk about common log, LOG, common log is understood to be in base 10. Base 10. So, for example, when you go to your calculator and you just type in log of 10, did you enter a base? No, you entered no base. Now, what I said a second ago is the base and the argument, when they're the same, what should be the solution? Push equals. What do you get?
1.
You get 1. Here's why. When you are talking about just log of something, just common log, LOG of something, it's understood to be in base 10. It's understood to be in base 10. So, in any situation in the future, if they want your base to be something different, they have to put the number there. If they put no number there, it's understood to be common log. Okay, LOG. So when you see, in your notes, when you see LOG, they're not going to have base 10. You'll have it written simply as log of x. Understood being base 10. If it's in any other base, I used to have to do the change of base formula. But you don't have to. You have a calculator that will do it for you. And that's the last thing we're going to do to finish off this lesson. But I would be remiss in making sure you don't understand what you're finding when you go just typing stuff away in your calculator. So let me explain. I want you to make the connection back to exponents. What does this not have? It doesn't have a solution. It doesn't have it equals some number, does it? We're doing it in our head. Let me explain. When we changed this to exponents, didn't we do the base of the log becomes the base of the exponent? And then we did the loop. So in my brain, I'm thinking to myself, 7 to what power equals 49? 7 squared does. 7 to the second power equals 49. So guys, what is log base 7 of 49? 2. That's your answer. You did it in your brain, okay? Because you understand what it's doing when you're solving the logarithm. 7 to what power equals 49? Okay, look over here to the right. What's that saying to you? 3 to what power equals 27? Cubed. So what's the log base 3 of 27? 3. Because that's what you're doing when you're solving a logarithm. Essentially, you're considering it as an exponent and you're trying to figure out, what is that exponent? 3 to what power does equal 27? Okay? 12 to what power does equal 1? And I could go through all these. 10 to what power equals 100? Again, how come I knew to say 10? Nothing written. It's understood to be base 10. 10 to what power equals 100? That's what this is saying. This one says 2 to what power equals 64? This one says 3 to what power equals 243? Get the point? And that's what we're finding when we find the logarithm of these values. Okay? Yes, sir. You had a question?
Yeah. So why is 10 the default log?
Because it's the one that they use the most, and they base everything around it. I guess it has to do with decimal value, because as you expand 10 in either direction, you're dealing with 10, 100, 1,000, or you're dealing with 10, 1, 0.1, 0.01, like that. Okay? Now, let me show you in the calculator how we're going to do this really fast because you guys have a speedy way to do it. Now, number 15, how do you think you're going to do that one in your calculator since it's base 10? You're just going to push the log button. The log of 100 equals what? 2. But for any of those where they change the base, here's where we're going to go. Y'all ready? You're going to go alpha, window, number 5. It does the change of base formula for you using alpha window number 5. So remember how we answered number 13? Log base 7 of 49? Let's see if it's right. Log base 7 of 49 equals 2. Is that what we said a minute ago? So sure enough, that's the answer. See, 7 to what power equals 49? Well, 2. Okay? So anyways, that's how we're doing it with our calculator. So y'all can go through these. We can go as fast as you could want. Alpha window number 5. I'm over here to the right. Log base 3 of 27. 3 to what power equals 27? The third. So 3 is my answer. I'm going to go down below that. Alpha window number 5. Log base 12 of 1. 12 to what power equals 1? 0. That should make sense. Didn't we say anything to the 0 power is 1? Okay, scroll down. Number 18. Alpha window number 5. Log base 3 of 243. What that means is 3 to what power equals 243? 5. I want you to not only understand what you're typing into the calculator, but what does it mean? Okay? You got to keep that connection between exponents and logarithms in your brain. Alpha window number 5. I'm looking at number 17. Log base 2 of 64. 2 to what power equals 64? 6th. And that's what you're finding when you solve these logarithms, okay? Last two, alpha window number 5, log base 9 of 1 over 81. So 9 to what power equals 1 over 81? Well, think about it logically. Isn't 9 squared 81? So what will be 1 over 81? Negative 2. Boom. There it is. Now, Aiden, let me go back to what I told you earlier. I told you that your base of your log will never be negative, right? And your argument, but can you have a solution that's negative? Absolutely. Okay? Just like this. And then finally, number 20, alpha window number 5. You got log base 64. And here's where this really comes in handy. It's harder in your brain to go 64 to what power equals 4? Well, it's getting smaller, so it has to be fractional. So the answer is 0.33 repeating or 1/3. Y'all remember how to change a decimal to a fraction? Alpha y equals number 4. See how it says F to D, D to F? It'll go in either direction. So sure enough, 1/3. So there it is, guys. That is how you do it. We've done 4 things quickly. We connected exponents to logarithms. 2, you can now write logarithm as an exponent. 3, you can write an exponent as a logarithm, correct? And 4, not only do you understand what you're doing when you're solving a logarithm, but you know how to go to your calculator to do it. Okay? So, tonight's assignment's a little bit of an outlier because it's 21 problems. But people are doing it in like 4 minutes. So I don't feel bad about giving you guys 21 problems because you can do them in like 4 minutes. It might take a couple of you guys 5 or 6 minutes.
We're doing all 21?
Yeah, it takes 4 minutes. You'll be done way before class is over. Yeah, you want to do it right now?
Yeah.
Absolutely. All right, so there you have it. Let me shut this video off before I forget.